exactly what I had to say, but I hope it was, I'm sure it was nice. I want to thank you for the kind invitation to come and talk about something that I think we all share a love for, and that is teaching and helping students learn. What I'm going to try to do today is to give you a sense of some changes that are going on in the United States with respect to chemical engineering education. Things are changing rapidly, both in the marketplace as well as the student body that we're getting to become the next generation of chemical engineers. And as a result, I think you'll see the curriculum and teaching methodologies change as well. I'm going to start with my last slide, and so that make sure you get the message I'm trying to deliver today, and that is the following. We know what we should be doing in education, engineering education in general, including chemical engineering education. What we don't know how to do, though, is how to change, how to incorporate it into our mainstream curriculum, how to affect all students with these changes. And that is the true challenge. What to do. I know what methods work for teaching, what information should be taught, what skill sets should be delivered, mainstream institutional. That's my main message today. Let's take stock of where we're at. What do we know? What is clear? We do know that the discipline is very strong. How do we know that? Industry hiring practices, for example, are very clear about that. Since the beginning of the profession, at least when we started recording salary data, chemical engineering has always been the highest starting PS in the last 50 plus years. That's probably the best evidence for a strong disciplines in terms of local output. That is, our customer industry likes that. We also know that the industry where our students are going is becoming much more diverse. It started with, of course, the basic chemical and petrochemical industry. In the 70s, we saw it expand out into the electronics industry. In the 90s, and now the life sciences and that industry is starting to take a foothold in the discipline, as well as other areas such as financial engineering. So if we look at the hiring practices by industry, this is data published by the AICHE in 2001. Unfortunately, they stopped taking this kind of data. But you can see that the chemical industry is less than a quarter of the hiring of U.S. students, and it's probably decreased even since then with all the consolidation that's been going on in the industry. Fuels is small as well, although it's starting to grow with the emphasis in alternative energy. It carries through into the PhD market, as you can see here. The electronics industry, which is dominated by PhDs in the hiring, count in 2001 for about 30% of the hiring. 20 years prior to that, it was non-existent. We also know in the transition that took place in the 50s and 60s to a chemical engineering science base remained valid. That has allowed us to apply chemical engineering science to a variety of technologies and a variety of industries. We also know, however, that life sciences is emerging as a fourth leg of the stool that we stand on. And we are trying to figure out how to introduce life sciences into the curriculum. We also know that a lot of the opportunities that come from chemical engineers is because we understand molecules. We understand changing molecules. And the quantification, for example, of biology has occurred because we are now taking that quantification down to the molecular level. And so we need to introduce more of a molecular basis into our undergraduate curriculum. We also find that our students are going more not into process engineering, but also into product engineering. They're making widgets. The chip is a good example. Chemical engineers are being called on more often to do systems. The financial engineering is really just a systems approach to a particular quantity called money. We're finding we're also having, because of tools advancing, we can look at new problem solving at multiple scales. We can techniques to do quantum mechanical calculation very routine, and many graduates can do it. Calcium, for example, at the molecule level. And we can go and look at grander systems, all the way to plants of plants, for example. We find also interfacial phenomena is creeping in more often. Much of our advances are taking place because we are being able to engineer interfaces. The whole area of nanotechnology, for example, is an example of interfacial engineering. The research prospects are about as bright as I've seen in my 30 years on faculty. The opportunities are just tremendous. Clearly, energy is going to be one of the grand challenges of the future, and who better placed to contribute to the solution of those problems than the chemical engineer. We also look at bioengineering. As I indicated, it's the quantification of biology that has allowed the opportunities for engineers, chemical engineers specifically, be it metabolic engineering, be it pharmaceutical, be it tissue engineering. Chemical engineers will be at the forefront of that. Nanotechnology is another area. There's a lot of research to be done. Catalysis probably being the oldest nanotechnology. Again, chemical engineers are there. Even in the information area, chemical engineers are contributing. So the picture for the discipline at the research basis, which would speak to the subsequent industry days, is as bright as I've seen it. The practice of chemical engineering is rapidly changing. We know that. The data I showed you on jobs placement, for example, is clear. Also, we find that where students go to work nowadays, they don't go to a single career. They're going to have multiple jobs. They're going to have to adapt very quickly. Many of the opportunities for the expanded industry are quite different, but yet we still have only the 4-year preparation time to prepare them for that workplace. The practice of chemical engineering education, however, hasn't changed since I was a student. Perhaps for my advisor as well. There was a transformation that took place in the 50s and 60s where we introduced the chemical engineering sciences. And we've only made minor changes since that time. That speaks, first of all, of course, to those foundational chemical engineering sciences being valid. But if we go and look at the methods that we teach, they have not largely changed either. So if you look at how we teach, it, for the most part, hasn't changed over 50 years. Well, we certainly haven't changed that much. If you look at the discipline as a whole, the discipline that commands the highest salary, has the research prospects, has the highest PhD to BS ratio. You would think that would be a vibrant, healthy, and very desirable degree discipline to be had by students. Our enrollments remain relatively small. Where it used to be the number 3 in the role, the discipline years ago, we're now down about 5 or 6. So the enrollments haven't kept pace with the supposed interest and reward for pursuing a degree in chemical engineering. There is a shift going on now where the students are coming with more of an interest in green. Again, you think they would be drawn to chemical engineering, but for some reason we haven't been able to convey the excitement that chemical engineering has to these new students. We also go and look at our discipline, and retention of students, at least in the U.S., is the lowest among all engineering disciplines. And I've got some data to back this up. We happen to have in our group a database of all the student records from 9 universities from 1987 to the present. That's over 400,000 student interest in there, and they're major engineering colleges. So we've been able to take this database and probe it and ask questions that you could not ask before because of the large number, and that would ensure that we had statistically meaningful populations. So this is a plot here of student flows, and what I'm plotting here is where students begin. Here's where they begin in chemical engineering, civil engineering, etc. And then where do they graduate from? And you can see of the students that begin in chemical engineering, only 55% graduate in chemical engineering. And the diagonal here is the number for the other disciplines. Again, we're the lowest in total overall retention. Where do our students go? Well, in terms of going to other engineering disciplines, they tend to go to industrial engineering. But more than a quarter of them leave engineering totally. And where do they go? Well, again, here's the beginning, and here's where they're going outside of engineering. Not surprising, most of the chemical engineers who leave are going over to physical sciences. Chemistry probably being the prime example. But again, we have a very high number of students attending the league. Are our students not as bright to begin with? Is that the issue? Again, we were able to probe SAT scores, high school GPAs, performance in calculus, etc. No, they're brighter. Our chemical engineering students, on average, starting out, are brighter than the other engineering students. Yet, they are not staying in engineering. Next question might be, well, we're tougher in chemical engineering. Right? We give more difficult classes. We grade tougher. We get rid of the weak students. Well, if you go and look at the data, here is the GPA distributions of students who leave in the third semester. This is their sophomore year, and those who remain. And you can see, yes, those students who have below a 2.0 are roughly leaving. But you can see, if you integrate this curve, more students are leaving who don't have grade problems. And in fact, if you compare the distribution, you take the ratio of these two, you can see, relatively, it's the higher in GPA students who are leaving. If you go back and look a little deeper, it's mostly women, or a relatively higher percentage of women than men. You go do the qualitative study, and you ask the students, why did you leave? They don't know what chemical engineering is. They're not excited about it. They want to make a difference. They're not sure chemical engineering is going to do that. We have all the pre-disciplinary chemistry that we take that prevents us from introducing chemical engineering early into the curriculum, and they tend not to stay around and wait for what the answer is going to be. We look at the student non-engineering flow into chemical engineering, and so these are students who have begun in the other sciences and other non-engineering degree programs. We get a very small inflow from outside, as of course we know, which we expect. Again, our chemistry requirement probably precludes people from transferring in, because if they don't start taking the sequence early, they will be too far out of step to having a relatively short time of graduation. So, this became a concern to many of us in the United States. And in 2002, a group from industry, from government, and from academia got together with funding from the National Science Foundation and the Council for Chemical Research and tried to get together and determine what would be best for chemical engineering education in the U.S. And we had a series of workshops over a period of 2002 to 2005. It was led by Bob Armstrong, who was then chair at MIT, the Chemical Engineering Department, and there's material posted on the website there. But part of the workshop, the major output of the workshop, was to envision what the future curriculum will be in chemical engineering. It began with the notion that chemical engineering is really the discipline that is at the center of the molecular sciences and engineering, the applications. So we set and are able to integrate the more molecular sciences as well as the engineering. And that is our role, because we understand molecules, we understand chemistry. We're not phase dependent. We don't just work with solids. We don't just work with electrons. We don't just work with cement. We work with all materials. We understand the molecule. We understand the complete complex chemical plant. And only chemical engineers can do that. And that's our role, is to integrate it. But yet we don't teach at all those levels. We don't teach at the molecular level. We don't teach at the complex systems level, other than the plant level. And so we aren't teaching what our true mission is. And that was what the group concluded and set out to rectify, or at least to propose. Some of the challenges for the curriculum were concluded is that we needed to integrate biology appropriately as a basic science. We had to have that as a stool for our science and math life. We needed to balance the need to have a very strong core, that chemical engineering science base. We need to retain that. That's what validates us. Other disciplines don't have such a strong core as we do. At the same time, we need to expand it. Our research is not aligned with what we're teaching as examples. We need to do a better job of showing that diversity within our examples of our teaching of our core. We need to balance the ability to teach very specific topics, the elective courses we have, with the need to educate students for the future, to be right thinkers. We needed to have a balance between fundamental knowledge, synthesis, and analysis. And finally, we need to attract our very best minds. When we surveyed our industry friends, you know, the one thing they liked about chemical engineers, they were smart students. It's not so. If biomedical engineering attracts the smart students, we will probably go hire biomedical engineering students. They're after the very brightest students. So it's a combination in chemical engineering of having very bright students, along with the foundational chemical engineering sciences that is what is attracted to industry. So the vision for this curriculum called for changes in science in the marketplace, called for changes in the curriculum. Everybody agreed on what those attributes of in a broad sense, what they should be for the chemical engineer. We believe that we had to add biology to our sciences. We also felt that there was a new set of organizing principles that included molecular transformations, multi-scale analysis, and systems. And expand on that. So molecular transformations, what we needed to do was to integrate chemical and biological, and we needed to span that across all levels. We needed to do multi-scale descriptions. Well, go back to the first one. The curriculum that I took, and largely teaching today, has very little molecular content. We went to graduate school for that. But with the tools that we have now, students at the undergraduate level can easily grasp it. And if we can furthermore integrate it with the chemistry that they're taking as part of the core, perfect time to begin that molecular introduction. Multi-scale description, the old core, we basically had continuum, macro to continuum is what we were teaching. We needed to drop back to the molecular and also go to the super macro that we could do now with the tools that are available. Systems analysis and synthesis, the old core had largely do the capstone design of a chemical plant. We need to work at all scales, again, from the molecular to the more complexity. We need to introduce the human factor, uncertainty, risk, other external factors into how we do systems analysis and processing, product synthesis and design. And the curriculum is envisioned. There's more detail for the website. I won't go through it, but it basically calls for taking these three themes or threads and integrating it throughout the curriculum. The molecular scale transformations, the multi-scale analysis, and the systems, starting with very basic stuff, for example, introducing a molecular basis of thermodynamics, to introducing it into our constituent equation for reaction engineering. In the beginning, we also needed to add the biology. At the same time, and very importantly, we needed to add an experience at the freshman level to excite students towards chemical engineering. We have been, there are attempts now over the last 5 or 6 years to introduce product engineering into the curriculum. I'll give you an example in a few minutes of that. But we also needed to pay more attention to pedagogy, how we teach. If we go and you do personality testing, for example, of our students, they're not like us faculty. The faculty have a very particular type of personality on average that's a fairly tight distribution compared to our students. Students learn often different than how we learn. And since our goal is student learning, we need to adapt our teaching methodologies to reach out to all student types of learning. And specifically, there's various techniques such as active learning, explicit skill development, combinations, as I indicated, of different learning styles, and integrating this both vertically and horizontally. What I'm going to go through now is give you a few examples of the kinds of things that we did in the Succeed Engineering Education Coalition. As Chen Ho indicated, this was a program funded by the National Science Foundation that was lasted for a period of 10 years, with about $10 million of funding each year to affect systemic change in engineering education. It wasn't just limited to engineering, chemical engineering, but it was broadly engineering education. This particular coalition, of which there were 5, involved students in the southeast of the United States. It included schools that indicated there, but it enrolled over 28,000 students, and 1 out of every 13 engineering degrees in the U.S. came from one of these 9 universities and colleges of engineering. So just to give you a little bit of a brief introduction of what the model was, we started with the student. The student success was what we were trying to identify. We also had a viewpoint that the student learning was not just in the classroom. That a more holistic approach. When a student goes off to a university, they of course take classes, they get involved in student societies, they have to adapt to a new living environment. They may get involved in an internship, a co-op. They have to possibly learn how to interview. There's a community there, so that it's the whole experience that you want to orchestrate to maximize student learning. What do we believe? Well, of course, we felt our students should be technically competent, and some of the attributes we came up with are indicated here. They're roughly the A through K that you now find in our ABEC criteria. So we would then take these key attributes. We would take our curriculum model, which is a holistic approach. In terms of content and structure, we focused on subject integration. We focused on early design, particularly at the freshman level. We also focused on multidisciplinary design, particularly at the capstone level. We also felt that engineering practice needed to be introduced. We had a very good engineering science content, but the practice component had been minimized. In addition, we tried to discover ways to do explicit skill development, communication skills, teaming skills, etc. It's always says, oh, we do that. It was almost not explicitly with them. And again, focus on faculty and faculty pedagogy, and faculty development. Processes and systems that we use to enhance student learning, faculty development turned out to be a key. We put a lot of effort into programs that would help faculty improve the art of teaching. We also toyed with the use of technology. I would say in retrospect that our endeavors in trying to enhance student learning with technology were not as successful as we had hoped. We thought it would be an inexpensive way to reach out broadly and more effectively to students, and it turned out that that was more difficult to achieve than we thought. We also investigated various methods of support systems to allow students to become successful. In particular, we looked at bridge programs where we bring students in early and do leadership training and other skill set development to allow them to become successful. And this was before ABET 2000, the new criteria when we first started. And we were called the Continuous Improvement Coalition because we were trying to adapt industry improvement techniques for improvement. Total quality management, continuous improvement, some of the names they went by then, into the curriculum. And out of that, this coalition can give credit for catalyzing the new ABET 2000 process, whether you like it or not. So let me talk about a few of these things. Let's talk about engineering practice, and design probably being the most example. We experimented with horizontal design. That's getting different disciplines together, for example, for a senior capstone course. We looked at real-world problems, bringing industry in, and using them as the basis, provide the basis for our design problems. We looked at multi-university, doing it virtually. We looked at service learning, which has become very popular in the United States. We also looked at team internships, where we send out a team of students rather than single students, along with a faculty coach. Entrepreneurship, virtual corporations were very successful. Students would form companies. Most of these companies, a majority of them would actually become registered and become real companies, believe it or not. And we also looked at alternative approaches, vertical design, where we would have design teams that would have freshmen along with seniors involved. Early design, where we would do design at the freshman level. Immersion, where we would do nothing but design for a whole term. Evolving design, where a student would have the same design project for 4 years, and as they would learn more, they would do another piece of the particular design. As an example of immersion, we had an immersion course called Process Engineering, which chemical engineers were involved, but also mechanical engineers, industrial engineers, and environmental engineers were involved in this. Students would go for a full semester, a summer semester, and do nothing but take one course. 112 credit course called process engineering. They were just like they were going to work. They come in at 8, they leave about 6 at night. They would maybe come in and take an hour in the lab, they'd come see a half-hour lecture, go into a study group for a half hour, and then go back in the lab possibly. Every day was different. Different instructors would come in. They had a studio that they would work in. They were completely immersed in, much as someone might learn a language. We have evidence, there's a few topics that they teach listed up here. We have strong evidence to suggest that the amount of learning that took place relative to taking separate courses that were segmented and possibly taken at different times was about double. That is, when we come back and test them after the fact and compare it to the group who didn't take this course but took the individual courses, we found that we had more learning that took place. Let me give you another example. Integrated product and process design. This was a 2-semester capstone design course, 3 credits each semester. We took students from all disciplines, including business. We would form teams of 5 or 6 students, which would have to be a minimum of 3 disciplines. We'd take a problem that was given to us by industry. Industry would give us $20,000. The faculty member, who was a coach, would get to keep the $20,000 and do whatever they wanted to with it. And so they were incentivized. And they would take a problem that industry wanted done but didn't have the engineering power and workforce to do it. So it was a meaningful problem to them. They were going to also spend time with an industry coach, and we spend roughly a day a week with the team. And they went about a very rigorous and methodical lecture series to learn how to do this, but they also had their own space to do prototyping, to work as a team, and they worked on it for a full semester. It was a very successful program. The student won because they got a real design problem. They would use it when they, in fact, interviewers were asking, did you go through this course? Because it was viewed by industry so positively. Industry would win because they got access to very, very inexpensive engineering. They also got to check out their future employees. About 85% of the products or processes that were designed were actually implemented. And the faculty also won. Not only did they get the $20,000 support for the semester, but they also often got some follow-on research. So today, this project has been going on for about 12 years. About 20% of the students in engineering take this course. And chemical engineers are actually a little bit more in number. Been extremely successful. Focus on student success. These are the support groups. In the United States, we have a very diverse population. So working with minorities is very important to us. We also are stopped at about 20% in terms of women in the United States. And that is also a challenge. The key thing that we tried to do was to introduce engineering as soon as possible. Try to get students an understanding of why they came into engineering. And compared that to probably, at least what I went through, our students weren't getting any engineering courses often until junior year, sometimes or late sophomore year. So we looked at a variety of ways to do it. Early design, equipment dissection, one chemical engineering-led example was to take processes that had photons involved. It could be a copy machine, a CD player, and students would go in there and actually tear it apart. And they'd have to write a manual on it, how to put it back together. And then they'd also go in and do an improvement on it of some kind of design. This is a freshman. Very successful. The students love it. And surprisingly, in this one example, the English department was the department that had adopted the course. They actually took over the course because it gave students something to write about, engineering students, that they had an interest in. And so the course is actually now being taught as an English course. Another example that we did was fairly simple. Was was to take the freshman course. A typical course in the United States is to take the department chair of each of the disciplines and have all the freshmen go into a large lecture room and have the department chair talk about what the discipline is all about. And the students would sit there and read their newspaper and basically not pay much attention. So we took that same one credit course, and instead of putting them into a lecture, we put them into a laboratory in each of the disciplines. So they would go and spend 3 hours in civil engineering, move on to 3 hours in mechanical engineering, and move through the various disciplines and actually do some laboratory experiments. In civil engineering, they take sticks and make a bridge, and the winner who would take the most load would get a prize. Well, we had a very large population. We took a number of students and put half of them through the laboratory base and half through the lecture base. And what we did was measure retention. So what we're plotting here is the percent of students in a particular cohort that remained or graduated in engineering versus those who didn't. And you can see the difference here is about a 50% increase in retention and graduation for those who took the laboratory-based course versus those who did not. And if you look at minorities and women, it's even strikingly greater. Again, going back to the original contention that the students in engineering are leaving engineering not because they can't do it, because they are not excited about it early on. As I indicated, we also tried to look at technology. We had a few successes, but some of them were not successful. One of the successful projects we had was on one of our campuses. We took an on-campus power plant that was being built, and we outfitted it so we had access to all the data, all the sensor data. And we also had a room installed for teaching that was in a control room on this plant. Now, this particular plant managed not only the energy, but it also managed the hot water. It was a cogeneration facility, so it was used for heating. There was also chilled water being pumped around for cooling, and then it had wastewater treatment. So it was really a set of facilities in there that could be used on campus to demonstrate what engineers want to do. And there was a utility interface developed that basically took all the data. So you could, for example, go in and watch a heat exchanger pop, and you could collect the data over time. Or you could see a control valve freeze and what happened. And you'd have the real data there. And students could see how you could become overwhelmed with data. And they could go there and watch the system. They could see a control operator. And they could do this in a freshman level if they wanted to. Turned out to be a very successful program. And this data then was made available on the net so that others could use it. The success factors. The Succeed Coalition was perhaps the most successful of the coalitions in terms of the amount of institutional change that we have. Each of our campuses have a substantially different engineering student experience than we had before Succeed. And there are several keys to causing changes to particularly in an educational institution. But some of the key factors are indicated here. Critical is faculty buy-in. If faculty didn't want to do it, it wouldn't get done. And so our faculty development program turned out to be most useful. By the time we were done with the coalition, we had about 80% of our faculty participating in some form of faculty development. Acceptable costs. There's a lot of things that will work. They're great to do, but we just can't afford to implement. And so developing things that were cost-effective was a true challenge. We also found that partnerships were important. The cost of change can be reduced through partnerships. So if we develop, for example, all the data from that power plant, now if we could exchange that over the internet and engage faculty from multiple universities to help develop modules to teach from and share those, the cost of that implementation, that change has been reduced. Administrative buy-in is also important. The education is not always the top of the administrators' list of priorities. And if you don't have the administration buy-in, it's very difficult to get the faculty buy-in, get resources, and that can lead to cause change. It also has to be high quality. You have to show it makes a difference. No one's going to change it if it's only marginal difference. You have to show a significant improvement. And in that sense, assessment and evaluation become important because we're engineers, we're quantitative, we want to see if it really make a difference. So let me give you another example of something we did with our database. We were looking at all the math, physics, and chemistry prerequisites that engineering students take. And this is at a particular university. So we looked at all the courses that students in engineering would take. The honors courses, the regular courses, the pre-courses, the pre-calculus, the pre-chemistry courses, and as well as the required core courses in chemistry, physics, and math. And we asked ourselves, which courses make a difference to graduation? And the way we asked it was we computed what is called an odds ratio. And so we asked if a person had a 1 point, all the things being equal, had a 1 point GPA higher, what was the odds for them graduating relative to the person that didn't have it? Because we had on the order of about 30,000 students at this institution, we could do this statistically significant. And so what we found was only 6 courses made a difference. Were significant to graduation. In other words, if you didn't do well in this course, you had a significantly poor chance of graduating. Or if you did better, than your neighbor, you would have a significantly higher chance of graduating. Most courses are listed there. This is a particular university. As you can see, 3 of the courses are labs. That's interesting, isn't it? Suggests that, again, the hands-on, active learning at the early stages of chemical engineering, of engineering as a whole, tend to excite students and have them prevail, or give them the encouragement to prevail until they get into the full discipline curriculum. It's also interesting that physics is not on this list, and perhaps because they were doing such a good job in physics, but perhaps in this institution, chemistry might be a problem. They're not teaching well. They're not teaching the average student very well. So it's, again, once we had this kind of data, we could go back to our colleagues in chemistry, physics, and math and work with them to try to affect that change. All right, I want to end with a couple of recent changes that are kind of on the horizon here. First, I want to talk a little bit about ABET. Asked that I give you an update of what's going on in the U.S. and ABET. And the Graduate Education Network of the Council for Chemical Research is also involved in looking at education issues. And I'll give you the results of a couple surveys we got. I'll close my remarks. So one thing that's a real hot topic right now is dual level accreditation. Dual level accreditation is accrediting both a bachelor's degree and a master's degree. When ABET was formed in 1932, it was said you could only accredit 1 degree program at each institution, either a bachelor's or a master's. At that time, there was a master's only program, no bachelor's that were being accredited. Some disciplines had as a final degree master's degree, so they were accredited. But over time, they've evolved to almost all institutions accrediting only their bachelor's degree. There's a movement led by the civil engineers to have the terminal degree in engineering be the master's degree in the U.S., not the bachelor's degree. And there's also a movement in the West of getting online degrees in engineering. University of Phoenix, for example. And those folks want to get their master's, they're particularly big in the master's degree, they want to become accredited. And so that's who's leading the charge there. The rationale for not having dual level degrees are listed here. First of all, it's expensive. It takes a lot of time to do the accreditation process. Now we have to do double. What are the objectives, the learning objectives going to be for a master's program? We maybe know what they are for an undergraduate. Engineering enrollments are flat. Even though demand is high, they are flat. Requiring a 5th year as a standard terminal degree might even encourage more students not to go into engineering. Employers can't get enough of our students. They hire multiple, the students are getting multiple offers. Apparently we have a pretty good product. It's not broken, don't fix it. The deans of the colleges here in the U.S. got together and strongly recommended that ABET not look at the prohibition on dual accreditation. So with that background, why did they want to do it? Why do they want to? Well, the two basic reasons are listed there. The engineering is becoming more and more complex. We need a terminal master's degree to be able to prepare our students minimally for the workforce. And secondly, institutions and programs that offer a BS master's deserve to have the opportunity to have it accredited. Again, this is mainly going at some of the online universities as well as the civils and environmental engineering. The outcome, which was just a matter of a few weeks ago, was the ABET Board of Directors now has changed their policy, long-standing policy, and they do allow dual accreditation. It's not mandatory for masters, it's voluntary, but what will happen, of course, it's not mandatory at the bachelor's level, but everybody feels compelled to do it. So we're thinking now is that time it will evolve and become essentially, by peer pressure, mandatory. International accreditation has been on the table. International accreditation in the past with ABET has been, ABET will help other countries implement an accreditation program, but they won't do it. Each country should develop their own process. They have had some interactions, some memorandum of understanding. They've also been able to establish an equivalency, but they really haven't been doing it. So the ABET Board of Directors approved a plan for non-domestic accreditation. They got together in 2005 and approved a plan. They started holding visits in the fall of 2007, and they plan to expand this as well. Systems engineering is becoming a hot topic in the U.S. 8 societies, including the American Institute of Chemical Engineers, are pursuing systems engineering as accreditation. So I think you're going to see more of that. A lot of systems engineering programs are popping up at the master's levels in particular. If you go and ask the people who are on the receiving end of ABET, as faculty out there being accredited, on degree programs being accredited, we complain a lot. We complain a lot about the time required to do it, the cost to do it, and we also complain about the unevenness of the evaluator. The pool of people who are doing the evaluation in the U.S. is small, and their training is not as even, and so there's a lot of complaining going on. So ABET is in the process of trying to expand the pool and to develop their training. And to do that, they have developed a program called PAID that is just getting underway to do better volunteer training. A couple surveys that I'll end with. One, we surveyed the master's degree programs in the U.S. About 6 months ago. And what we discovered? Well, we found out there's a lot of new designer or specialty master's programs out there. Some of them are listed there. About 20% of the departments have them now. We also find that more departments are going to a combined BS-MS program where the student can start a master's degree while they're still an undergraduate, either in their junior or senior year. And there's some double dipping. In other words, credit offered both the bachelor's and the same credit as counts towards both the bachelor's and the master's degree program. We also looked at the curriculum of the PhD program, and what we discovered was that the 4 courses we teach, the math, transport phenomena, and thermodynamics, and reaction engineering are core, and they do remain core. But there are some new courses that are starting to creep in. In particular, the 4 at the top there, interfacial phenomena, advanced computational methodologies, polymer science and engineering, and possibly nanosciences are starting to become more core-like. We find departments starting to require these. The University of Washington is completely transforming its undergraduate degree program to become more molecular-based. And so they've got a real grand plan in that area. So let me leave with my final message. We know what we're supposed to do. We know we need to introduce engineering early. We know we need to become better teachers to teach towards our students that have an array of learning styles. We know we have to introduce more engineering practice. We know we have to take a holistic approach to student learning. We know we have to always improve. We have to keep evaluating ourselves. We know what we should do. We have experiments out there we can run. We know what works. The problem is how do we change? How do we institutionalize this? How do we mainstream it so all students get the improved experience and are better prepared to meet the challenges of the future? So with that, I want to thank you and appreciate your time.